balik na, no? We have to check na the section. This W14 by 90. If you try to look at in the AISC manual, the height of the web divided by thickness is 25.9. No? And you have to check the this value, no, to the limiting values. The web area is equal to the depth of the section times the thickness of the web. That is, since this is W14, try to look in the manual, the depth is also 14, no? Times the thickness, which is equal to 0.44. And is this one, we'll use this one later, no, in the computation of the nominal shear force. Yes, now we have already solved now the height to thickness ratio of the web. That is 5.9. Then we have to check for the leading values. So we have to check for 2.24 square root of E over Fy. So the modulus of elasticity of steel is 29 KSI, 29,000 KSI times the yield strength, which is equal to 50, no? And the answer is 54. Then comparing the value for the H over TW, T sub W. So this value is less than, no, the 25.9 is less than this limit ratio 54. So since this H over T sub W is less than this ratio, so the strength is governed by shear yielding of the web, no? And that is the C sub V is equal to 1.0 as pointed out in the specification user note. This will be the case, no, for most W shapes with Fy yield stress less than or equal to 50 KSI. So the nominal shear strength is equal to the 60% of the tensile yield stress, that is Fy, times the area of the web times the C sub V, no, as discussed earlier. For less than this one, your H over TW is less than this one, your C sub V is 1.0 and your resistance factor is 1.04 LRFD, and for the factor of safety for ASD is 1.5, no? This is for the wide flange shape with yield stress less than or equal to 50 KSI. Then right, so the answer now for nominal shear stress is equal to 184.4 kilo pounds. So we have to check, this is just the nominal, no, nominal shear force. So times the resistance factor, you will have your design, no, design shear force, no, which should not be your limiting, no, values. Dapat dili siya mo malagpasan, no. We have to solve, no, the ultimate or the maximum shear force, which is based on the applied loads, no. Then since this condition is less than 2.24 square root of E over Fy, your resistance factor now for shear is 1.0. So resistance factor times this nominal shear force, your design shear strength is 184.4 kilo pounds, no? This is your design shear strength. Dapat ang imong maximum shear force, or yes, which is caused by the applied loads, should not be less than should not be greater than this design shear strength. No? And from the example, the um, uniform load 5.6. Yes, this is simply supported beam subjected to uniform load, no dead load, including weight of the beam, and live load W. This one, how to find this one? This one is the W sub U, the ultimate uniform load. That is 1.2 dead load plus 1.6 live load. So 1.2 times the dead load, which is equal to pila to 400. So zero point 0.4, no, and 1. That is zero point 0.4 plus 1.6 times 1 kilopounds per foot. So the answer now would be, my calculator, compute this 1.2 times 0.4 plus 1.6. Sorry, 2.08. That is 2.08 kilopounds per foot. And the L is given approximately 45 feet. For a simply supported uniformly loaded beam, the maximum shear occurs at the support and is equal to the reaction. Yes, if you have the simply supported beam, now you already know this one. I believe you encounter this one in your strength of materials and also in your theory of structures. Then you have the simply supported beam. Now you have the pin here and the ruler, so you will have the vertical reaction, that is, say this is A and B, so that this is R sub AY. Since you don't have any horizontal forces, so meaning your RAX is 0, no? RAY, and this is your RBY, no? For simply supported beam, the maximum shear occurs at the support, diba? This is how to, if this is W and this is L, the support reaction, this is equal to WL over 2, no? This is your maximum shear, no? Of course, at the support. So, munang the B sub U or maximum shear is WL over 2, or the uniform load 2.08 times the length of the beam divided by 2. And it was found out that the answer is less than the design shear strength, which is okay, no? So this is okay. This is for LRFD solution. For ASD solution, we have to use, no, the safety factor omega for shear. Since this H over TW is less than 2.24 square root over Fy, you have to use the safety factor equal to 1.5, no? So that the allowable shear strength is equal to 123 kilopounds for ASD. This is your limiting value, meaning the shear force, no, caused by the applied loads should not be greater than this allowable shear strength. So by ASD solution, to get the total, no, uniform load, you just have to add, no, the dead load and the live load. So that is 0.4 plus 1, 1.4 kilopounds per foot. Then again, to get the maximum shear, which is at support, no, for uniformly distributed, simply supported beam, no, in load. It is always at the support, no, kung uniformly distributed ang load, no. This is the beam, you have the reaction, say RA and RB. So at the support, to get the value, this is W and this is L. Again, to get the reaction of that one, that is equal to WL divided by half, no? Divided by 2. So, manang WL over 2. So, the total service load, no, by ASB solution is 1.4 times the length of the beam, 45 divided by 2. And we will get 31.5 kilopons, which is less than the allowable shear strength. So, this is okay, no? Right. Alternately, a solution in terms of stress can be done since shear yielding controls. So, you have to use this is a B 1.0 and the factor of safety 1.5. Okay, we have the alternative solution. No? So, the allowable shear stress is 0.4 times the tensile yield stress. That is 0.4 times 50, 20 KSI. So the required shear strength is, excuse me, the shear force, the applied shear force divided by the area of the web is equal to 5.11 KSI. This 31.5 is the applied shear force ganina. This one, 31.5 kilopounds. Divided by the area of the web. The area of the web is the depth times the thickness of the web, which we computed earlier. This one, the area of the web is okay, this one. This is equal to 6.16 inches square. And remember that ganina we arrived with this 0.4 times tensile stress of steel for most cases of common case of hot rolled eye shapes, no? So if we try to solve using the alternative solution, we'll arrive that the applied shear strength is less than the allowable, no, shear stress, no, F sub P. So the answer is the required shear strength is less than the available shear strength. So the win is satisfactory. Note that the values of the resistance factor times the nominal shear force and this ASD na nominal shear force divided by factor of safety are given in several tables in part 3 of the manual. Now, if you to look at the ASC manual table 3, including the Z sub X table, so the computation of shear strength is unnecessary for hot rolled shapes. Let us see, no? Tanaw na to siya. This is the values of the design shear stress and strength, no? And the allowable shear strength. Kung tanaw na to sa table, that is table part 3 of the manual. That is table 3, no? Yes, like this one, the Z sub X. For FY equal to 50 KSI. Then you have the shape now in the first column. Then you have the values of the plastic section modulus, the Z sub x, and in the last two columns now of the table are the values of ASD, this allowable shear strength, and the design shear strength. No? Like for example, we have the sa itong section ganina W14 by 90. Atong tanawon 14 by 90. 68, this is level 14 by 68. Alright, this one, no? W14 by 90. So, naa siya the values for the allowable design strength and the design, yes, the ASD solution and the LRFD. 123 and 185. So that dili na necessary to compute, no, to following those procedures. But naana siya automatic sa table. Yes, this one, the design shear strength is equal to 185 kilopounds, which is the same with the value in the table, no? And sa ASD solution, 123, no? 123. Kung tanawin mo sa table, that is also 123. This is table 3-2. So, try to see the video that I'm going to post now. A discussion on deflection. I think I have to discuss that one in the C. That is deflection. So, deflection. Okay. Alright. Okay. Discuss taning deflection. No? So, deflection, since wala siya sa slides, no? But naa siya sa book. Now, kindly scan the book, no? And see this 5.9 deflection. In addition to being safe, the structure must be serviceable. So, atong gibuhat ganina, we check the strength of the section, but not only strength, no? We have this we gitawag nga serviceability. So, the serviceability meaning a serviceable structure is one that performs satisfactorily, not causing any discomfort or perceptions of unsafety of the occupants or users of the structure. So, kaning serviceability, we have to check in here the deflection of the beam, no? And for a beam being serviceable, usually means that the deformations, primarily the vertical sag or deflection, must be limited, no? For a simply supported, uniformly loaded beam, such as in the example, no, the maximum vertical deflection is this one. I believe you have encountered this one in your theory of structures. So, nani siya? This one. That is 5/384 WL to the 4th over EI. this is for the deflection, maximum vertical deflection of a simply supported uniformly loaded beam. And yes, this one. Like this one, this is the representation of the beam, no, with uniform load, and the deflection, no? This one is the deflection. This is the elastic curve, no, of the beam. So for uniformly simply supported, uniformly loaded beam, the maximum deflection is at the center. Diba? So the maximum deflection occurs at the center. So remember, we have to check the strength. That is, we did solve for the design shear strength and the allowable shear strength, and then we compare, no, through the effect of the loads. Dapat dili siya mulapas ato nga mga design limits. And we have to check also the serviceability, that is the deflection of the beam, no? We have this table now for the deflection limits. So for the maximum live load deflection of the roof beam supporting plaster ceiling, that is L over 360, supporting non-plaster ceiling L over 240, and not supporting a ceiling L over 184, floor beam is L over 360. Ang anong actually, in the computation of the deflection limits, we only account for the maximum live load deflection because the dead load actually is gi-account na siya sa camber. The camber means that kanang during the construction of the beam, no? Nana na siya camber daan. Camber is like, if this is the beam, gi-camber na siya. Meaning, di pa na kay this is actually the camber. We have the let's say bali ang beam ana nimo is gipa bulge na nimo outward, no, to account for the deflection of dead loads, meaning ang ato lagi ma-account ani, no, for the deflection is dili nimo ma-include ang dead load, instead only the live load, no? So like for example, we have this example, compute the dead load and live load deflections for the beam shown in figure. If the maximum permissible live load deflection is L over 360, is the beam satisfactory? Is the beam satisfactory? So we are given the beam, the section of the beam, W18 by 35. Now then you have to check, no, if this beam is okay, no, given nga ang maximum permissible live load deflection, no, take note this one, maximum permissible live load deflection is L over 360, no? So with this loads, no, dead load, live load, check, I mean, you have to solve for the maximum deflection of the live load only. So it is more convenient to express the deflection in inches than feet. So to the given, no, dead load and live load is in pounds per foot. So remember this maximum permissible live load deflection L over 360, dapat live load lang yun siya, no? So for the uniformly distributed simply supported beam. No, the maximum deflection is 5 over 384. So times the, okay, first is we have to solve for the dead load deflection. That is 5 over 384 times the dead load. No, this is a 0.5. No, divided by 12 to convert to inches, times the length of the beam, that is 30 feet, so times 12, no, to convert to inches, to the power of 4, divided by EI, so that is 29,000 KSI, times the moment of inertia for the beam. So this is actually, the I is actually can be found in the ASC manual, no, part 1 for table, properties, and section. So makita niyo siya. This is I sub I, I sub Y. So solving, that is 0.616 inch. For drive load deflection, you just have to substitute, no, the value of the given live load, that is 550 pounds per foot. So divided by 12 to convert to inches. The answer is 0.678 inch. And uh, the maximum permissible live load is L over 360. L, this is the length of the beam. So that is 30 times 12 inches divided by 360. The answer is 1 inch. And again, no, we are like instructed if the maximum permissible live load deflection, meaning we only have to account, no, for the live load, wala labot ang dead load. So if you try to compare, no, the answer for the live load deflection is 0.678, which is less than the maximum permissible live load deflection. So meaning the beam or the section, or this W18 by 35 is satisfactory. This is okay, or the beam satisfies the deflection criterion. Right, this is for the deflection, no? For the serviceability of the section of the structure.